Lesson 1.11 is on the efficacy of scientific notation. And really all efficacy means is it's just the ability to produce a desired or intended result. So basically we want to use scientific notation to help solve real life problems, especially when we're dealing with things such as like protons and electrons. Obviously this is an extremely small number. So let's review just how to put things in scientific notation. Remember, we have the decimal point. We want it between the first two non-zero digits. So this becomes 1.672622 times 10. It's always times 10. And then you basically count the number of decimal places. If you go from where you want it to where it is, 1, 2, and count correctly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Got a little dicey there. Our exponent is going to be 27, and since we were moving to the left from where we want it to where it is, it's negative 27. Again, you can think of that as a very small number. That's why it's negative. Doing the same here in the mass of an electron. I want to put my decimal point between the 9 and the 1. 9.109382991. Again, that's shorter than writing out all those zeros. Times 10. If you go from where you want it all the way over here, I believe I counted 31, so it's going to be a negative 31. All right, so we can use scientific notation to do problems with these types of numbers, these incredibly small numbers. And that's what it says here. When we wanted to compute how many times heavier a proton is than an electron, instead of trying to figure out this problem, we can figure out this problem. So you're going to see that. Oh, let's talk about this. We want to figure out how many times heavier a proton is than an electron. So how many times heavier, if we want to figure out how much times something, we have to divide. And so we're going to put the proton on top. And usually for what we're doing now, you're going to put the bigger number on top as you're setting it up. Is negative 27 bigger than negative 31? Yes, think of the number line. Where it falls on the number line, it's further to the left. But I want you guys to maybe make a little note on, okay, so if you are comparing numbers in scientific notation, you want to look at, if you want to know which one's larger, you basically look at their exponent. You say, whose exponent is bigger? So if it's asking you which number is bigger, you look at the exponent. The exponent, whatever one is bigger, that's going to tell you what number is bigger. Now, if they're the same, then you can go to the number out front. But looking at negative 27 and negative 31, negative 27 is bigger because it's further to the left on a number line. All right, so I'm basically just going to divide this problem right here. And remember, what we do is break it up at the time sign. So I get 1.672622 divided by 9.1093829, hopefully I didn't miss any numbers there, times, then we have 10 to the negative 27th over, nope, not what I wanted, over 10 to the negative 31st. So this should look similar to what we've been doing. Basically, you take a calculator and you divide this out, okay? 1.672622 divided by 9.1093829. Obviously, there's going to be some rounding taking place here. So I'm going to say that this is approximately equal to 0.8361553, we'll leave it there, times 10. Now be careful with the exponents here. It's dividing, so we're going to go negative 27 minus a negative 31. Okay, don't lose this negative. you're still subtracting them. So 0.1836, I'm just going to stop there for the sake of time, times 10 to the, subtracting is the same thing as adding the opposite, or keep, change, and we get negative 27 plus 31, which is 4. Just like before, though, we're not done there. This isn't in scientific notation. Scientific notation is a number between 1 and 10. So I got to put the decimal point there. This has to be 1.836. And then if I go from where I want it to where it is, I'm moving it 1 to the left. So this time I'm going to subtract 1. So if I'm going to the left, subtract 1. Again, getting bigger by a power of 10 needs to get smaller by a power of 10. So this ends up being 1.836 times 10 to the third. Whew. Or if you were to move this over 3 times, that'd be 1,836 approximately, because remember I did some rounding up here, times heavier. As small and as tiny as the weight of the proton electron is, a proton is over 1,000, pushing 2,000 times heavier than an electron is. This is the purpose of scientific notation. We can do different calculations and estimates with these really small numbers because we have a method to be able to do it with.